Okay, let's take a look at 12.6. I actually get asked about this one quite frequently. And it really boils down to that fun-filled counting that you guys love so much to do. Is telling you that the relative rates for these boxes are 1, 1, 4. So I'm going to write that up there. 1, 1, 4, 4. What they're kind of doing is they're using visual tools to walk you through a limiting rate problem. So you want to get the concentration of A and the concentration of B and B, both, in all your boxes. They're telling you that red spheres represent A. So I'm going to go through and I'm going to count my number of red spheres that I have in each one of those boxes. So let's blow these up real big. And I'm going to be looking at my red spheres here. So I have 3 red spheres here. Here I have 1, 2, 3, 4, 5, 6. 6 red spheres here. Here I have 3. And here I have 1, 2, 3, 4, 5, 6. 6 red spheres. Now I'm going to do the same thing for my B's. 3 B's here. 3 B's here. 1, 2, 3, 4, 5, 6. 6 B's there. And I bet 1, 2, 3, 4, 5, 6 B's there. What we're looking at is how changes in concentration affected the rate. So and we have to do so in such a fashion that we're holding the concentration of B or A constant. So let's take a look at experiment 1 and experiment 2. In experiment 1 and 2, the concentration of B is constant. Concentration of B doesn't change. However, our concentration of A doubles. Did doubling the concentration of A affect the rate? It didn't, right? The relative rate of experiment 1 and experiment 2 are both 1. So changing the concentration of A had no effect. We can find further evidence of this if we look at experiments 3 and 4. In experiments 3 and experiment 4, once again, our concentration of B is the same. Both have concentrations of B equals 6. We doubled our concentration of A, but yet the rate of 3 is the exact same as the rate of 4. So changing the concentration of A while keeping B constant had no effect on the different rates. When the concentration of a substance doesn't affect its rate, that means that we have 0 order in A. So we can say that our reaction is 0 order in A because the reaction isn't affected by our concentration of A. Does the concentration of B affect the reaction? Well, let's take another look. Here, we need to find one where we're holding A constant and we're changing the concentration of B. So we'd want to look at 1 and 3. And I'm going to create a little bit of, whoops, that's not what I wanted to do. Just a second here. There we go. So let's cover up 2 at the moment so we can focus on 3 and 4. In 1 and 3, we have the same concentration of A. A equals 3, A equals 3. Our concentration of B doubles, though. Does doubling the concentration of B have an effect on the rate? Heck yeah! 3 moves 4 times as fast as 1 when we doubled our rate. So we would say B to what power? Well, 2B to what power? We doubled our concentration of B, and we saw our our rate quadruple. What can we raise 2 to get our rate to quadruple? 2. So we can conclude that our reaction has to be second order in B. Can we find more affirmation of this? Well, if we now look at experiments 2 and experiment 4, in experiment 2 our concentration of A is 6, in experiment 4 our concentration of A is 6. So when we go from 2 to 4, concentration of A doesn't change. However, our concentration of B goes from 3 to 6. Our concentration of B doubles. And what do we see with our rate? Our rate's quadrupling again. So once again, we see evidence that B is second order. So we have a reaction where we are second order in B, 0 order in A. So the overall reorder of the reaction would be 2. And thus what you're going to do with this type of problem. It's fun counting bubbles!